In lesson 92, Paul explained the operation of the wait command in the Pico W PIO state machine assembler. The wait command can help us to capture the status of buttons and switches in our programs. As the name indicates, the wait command is a blocking command. Program execution comes to a halt when it encounters this command. Execution resumes when the specified 1 or 0 condition is satisfied. The syntax of the wait command is shown here. Polarity indicates whether the program should wait for a 0 state or a 1 state. SRC, or source, can be either GPIO, pin, or IRQ. An index is a parameter that we supply to SRC. If SRC is set to GPIO, index is the literal GPIO pin number. So if you said wait 1, GPIO 22, this would wait for GPIO pin 22 to become a 1. If SRC equals pin, index is the offset from the in-base pin. If in-base was 14, then wait 0, pin, 3 waits for GPIO pin 17, the third pin indexed from in-base, to become a 0. The use of SRC equals IRQ is outside of the scope of this lesson. Recall that we specify the first GPIO pin in our range of outputs as part of the state machine instantiation statement when we say outbase equals pin something, 12, let's say. In a similar way, the wait command requires us to specify which group of GPIO pins are in our range of inputs. We are also required to declare those pins as inputs and indicate whether they use pull-up or pull-down resistors. This is done by adding a clause to the instantiation statement as shown here. A complete instantiation statement might be as complex as the one shown here. Paul also demonstrated the use of no-op instructions as a form of debouncing. Our assignment was to create a 4-bit up counter which would increment on a button press, and the button was to be debounced. Here's the code. As usual, we start with imports. We import pin because we use the pin statement in the PIO instantiation. We import RP2 because we're going to be programming a state machine. I created a set of variables thinking this would improve program readability. Now I think it makes the code look cluttered. I may not do this again. The RP2 decorator on line 15 specifies that we'll be using out instead of set. We'll start by resetting our 4 outputs low and setting the shift direction parameter to right. The up counter function, which starts on line 17, is based on my code from the homework for lesson 90, which adds by inverting, decrementing, and inverting again. You can find a link in the description. This code will be downloaded to the state machine 0 when the MicroPython program runs. The wrap target label signals the beginning of the state machine program. The program holds the accumulated count in the X register and will start by counting from 0. So we set the X register to the inverse of 0, as shown here. The show count label is followed by a move instruction, which copies the inverse of the X register to the LEDs. Once the LEDs are updated, program execution moves to the wait statement at line 22. This wait statement is waiting for the pin which is offset by 0 from the in-base pin, actually pin 17, to become a logic 0. This is the red push button. This statement is waiting for the user to release the button. If no one is pushing the button or still holding it from a previous push, this will be true. The 2 no-op instructions provide some debouncing, and execution arrives at line 25. This wait statement is waiting for the pin, which is offset by 0 from the in-base pin, pin 17, to become a logic 1. This statement is waiting for the user to press the button. When the user presses the button, execution continues to the two no-op instructions, which provide some debouncing. Assuming that the X register is not 0, the jump instruction on line 28 will loop back to the show count statement and decrement the X register. The new value in the X register will be inverted and displayed. The waiting process repeats. Note that the wait statement on line 22 will prevent the LEDs from racing through the count if the user holds down the push button. Eventually, when the X register is 0, execution will fall through to line 29, the X register will be reset to 15, and the whole process will repeat. Line 32 is the state machine instantiation. It specifies which state machine we're using, the name of the function holding the assembler code, the in-base details, the execution frequency, and the out-base details. Line 37 activates the program in state machine 0. In the usual try except clause, we can see that the while true loop is empty, and that if the user presses Control-C, state machine 0 will be deactivated and the user will be advised that the program has stopped. And here's how it looks. Well, that's it for this assignment. Any and all comments are welcome. Don't forget to like or dislike the video before you go. And feel free to subscribe. Don't forget the notification bell. We'll talk to you next time.